Okay, so welcome to this live webinar on charging infrastructure management. As we know that electric vehicles are is a hype in the market. That means a lot of drive is there by the government, also by various types of industries to you can say. So some of there is some background noise in some of the students' mic. So if you can mute yourself, that will be good. Okay. So various industries and various governments, they are trying to push 50% of the transportation systems, or you can say, should be converted to electric vehicle. That is the aim or goal that most of the government and industries are trying to reach. Okay. So for that, charging infrastructure is a very important thing because just like fueling stations, if the fuel stations are correctly located, they are resourced properly, then there is no problem in driving the vehicle. Nor for you can say there will be no problem for passenger vehicles, nor there will be any problem for transportation vehicles. Because mostly transportation vehicles will face a lot of problem if the infrastructure is not properly installed. Passenger vehicles may not face any problem because within an urban area, mostly there are enough petrol stations, enough charge. Just like I'm saying about IC vehicle, in urban areas there are a lot of petrol stations. Hence, passenger vehicles they don't have any problem in refueling themselves. But transportation vehicles, vehicles that are used for goods transportation, logistic vehicles, they face a lot of problem because they have to travel between cities or between urban areas, and there is a lot of, as India is a very big country, so a lot of you can say a lot of empty, or you can say remote locations are there where installation of petrol stations and charging stations, generally petrol stations, are difficult. But still, since petrol stations are being installed from a very long period of time, most of the remote locations are also installed with petrol stations properly, so that the transportation vehicles will not be hampered that much. But if the charging stations for EVs, you can say transportation vehicles using EV technology, if charging infrastructure is not properly managed, then they will be facing a lot of problem. All the commercial goods will slow down, or the commercialization will slow down because it will take a lot of time to transport goods between cities, between states. Okay, if the charging infrastructure is not properly maintained, and there is another problem that we'll be discussing, that is the load. When a lot of electric vehicles will be running in the streets or in the road, then at a particular time or throughout the day, there will be certain periods where there will be a lot of loadings on our power systems, on our electric grids. Why? Because a lot of people will be charging their vehicle at that period of time. So when there is a lot of load, then we have to manage those loads also effectively, so that you can say power systems or power generators or generating units can provide the electricity properly, or they can manage the load, or else there will be power cut. A whole lot of difficulties will come if the load is not properly managed. So we'll discuss about those things in this webinar. If there is any problem, just say. Okay. Just say that, sir, I have this problem. You are not audible. Okay, some of the students, they have problem in English, so you can say there is a subtitle so that you can follow. If you are not acquainted with any of the accents or any with my accent that I am saying, there is a subtitle you can follow. If still there is some problem, then actually a lot of if I will not be saying in English, because there is no problem in saying Hindi. I have no problem in saying Hindi. Okay, but most of the students will not be able to understand Hindi. Okay, so some of the students, see, just when you will be connecting, just try to mute yourself because there is a lot of background noise. And I don't want you to, and all other students to get hampered because of certain noise. Okay. So the transition to electric mobility is a promising global strategy for decarbonizing the transportation sector. India is among a handful of countries that supports the global EV30 campaign, which targets to have at least 30% of the new vehicle sales by 2030. That means EV is also, India is also trying to reach or is also trying to convert nearly 30% of its transportation vehicles to or passenger vehicles to or nearly 30% of all the vehicles that are available in India to electric vehicle. An accessible and robust network of EV electric charging infrastructure is an essential prerequisite to achieving this ambitious transition. That means the charging infrastructure should be properly managed and should be first it should be installed at the required locations, and it should always also be managed properly. Because petrol station, you can say we have seen overcrowding of petrol stations during price hikes. Those things can happen. Okay, those things can happen because for charging your electric vehicle, it needs some time. Refueling needs some 5 to 10 minutes. Charging may need 15 to 20 minutes. So there may be a lot of traffic in those charging stations. Hence, to properly manage those charging stations is also a big problem. So how to manage those things? Let us see. However, given the novel characteristics of new infrastructure type, there is a need to customize it to the unique Indian transportation ecosystem and build capacity among the stakeholders to support on its ground expansion. A contextual approach is needed to ensure the efficient and timely implementation of EV charging infrastructure, such that it meets local requirements and is optimally integrated within the electricity supply and transportation networks. Okay, so let us talk about electric vehicle. How electric vehicle works, not how it works, not talking about how it works, but what is an electric vehicle and how it will be running on the road. An electric vehicle can be charged in a variety of ways depending on the location and requirement. Accordingly, charging infrastructure for EVs is of different types and designed for different applications. Specifications and standards for EV chargers is also known as electric vehicle supply equipment, vary from one country to another based on the available electric model in the market and the characteristics of the electric grid. So depending on the type of electric vehicle that is running in that country or in that state and the type of electric grid that is available in that country or state, we will be having various charging standards. Okay, so or charging protocols. So we'll also know about those type of protocols. So what are the things that are needed in any charging infrastructure? First is load management. Dynamic load management with configurable charging strategies. Then second thing will be charging station control. Third thing will be vehicle preconditioning will be available in the charging infrastructures or charging stations. What is vehicle preconditioning we'll be discussing. Vehicle authorization. That means that vehicle is authorized to charge or not. Okay. Then report generation. Okay. Report generation. Then depot management, clearing of the vehicles, and certification of charging. All these things are required, or these should be the features that are available, that should be available in all the charging infrastructures. Okay. Then EV power supply equipments. What are the various types of power supply equipments that are needed to recharge EV? EV electric vehicle supply equipments is the basic unit of EV charging infrastructure. The EVSC accesses power from the local electricity supply and utilizes a control system and wired connection to safely charge the EVs. An electric vehicle supply equipment or EVSC control system enables various functions such as user authentication, authentication for charging, information recording, and exchange for network management and data privacy and security. It is recommended to use EVSCs with at least basic control and management functions for charging EVs. That means any type of supply or any type of charging equipment that we should use, they should follow a specific standard. What is that standard? Let us see. What is that standard? You can see a specific standard that is written: 2 CCCS plugs and sockets, 1 plug and socket. Okay, 2 AC sockets. There are various types of sockets available for charging. So whenever you will be charging in a specific charging station, different types of vehicle will come. Some vehicles will be 3 kilowatt vehicle, 4 kilowatt vehicle, sorry, not 3, sorry, 30 kilowatt vehicle, 40 kilowatt vehicle, 80 kilowatt vehicle, big vehicles, or you can say various kilowatt vehicles will be charging. Generation 1 vehicles, generation 2 vehicles, generation 3 vehicles. There will be a lot of variety in electric vehicles. Hence, the charging stations should properly able to manage those things. Conductive charging or plug-in wired charging is the mainstream charging technology in use. Requirement for EV charge, you can say EV electric vehicle supply equipment for conductive charging depends on factors such as vehicle type, battery capacity, charging methods, and power rating. What is this conductive charging? We'll discuss. So battery specifications for different EV segments. EV charging requirements depends on the specification of EV batteries, as power must be supplied to the battery at the right voltage and current levels to permit charging. Remember, your charging, you can say a BMS is installed in all the electric vehicles. So if the BMS is uh, recognizing that the charging voltage and the charging current is not proper for this type of battery pack or for the battery pack that it is installed, then it will not charge. You will be connecting the vehicle, but it will not be charging. So you may lose some time. Okay, let's say you have connected the vehicle for 2 minutes, 3 minutes, and the BMS is not supplying any current. Actually, monitors are there that will show whether the vehicle is charging or not charging, but still, if uh, proper connections are not made or if the proper chargers are not utilized, then there is a problem. This is the reason why we have varieties of charger. The sockets that are available for different types of vehicles, they vary. Hence, we cannot use a different socket on a different vehicle. The vehicle, let's say 30 kilowatt vehicle, has a specific type of socket for charging. We cannot use the same charging socket for 40 kilowatt vehicle. Okay, or else there will be no charging, or actually we cannot connect. So there will be no charging. Typically, capacity and voltage of EV batteries vary among the different EV segments as shown in table. You can see in here table. That is, two-wheelers, the battery capacity is from 1.2 to 3.3 kilowatt hour, and the battery voltage is from 48 volts to 72 volts. For three-wheelers, 3.6 to 8 kilowatt hour, 40 to 60 volts. Then e-cars, 21 kilowatt hour. Tata Nexon that we see, that is 30, 35 kilowatt hour, 30 to 40 kilowatt hour. The new versions are higher, the lower versions are 30 kilowatt, 72 volts. E-cars, second generation. Actually, now we are at second generation. Okay, second generation e-cars. So they are nearly 30 to 80 kilowatt hour, and their battery pack voltage is 350 to 500 volts. The first generation of e-cars is also powered by low voltage batteries. However, these are likely to be phased out in the future, even if they continue in specific uses cases such as taxis. There is no fast generation car available nowadays. Though some of the regions, remote regions, they are using these first generation cars, but now they are all replaced with second generation. The second generation of e-cars, as seen in the upcoming e-car models, it is powered by high voltage batteries. Electric low commercial vehicles will comprise of both low voltage and high voltage vehicles depending on their load carrying capacity. Okay, LCV means light commercial vehicles. Then charging method. EV charging involves supply of direct current to the battery pack. An electricity distribution system supply alternate current power. A converter is required to provide DC power to the battery. Conductive charging can be AC or DC. In the case of AC, the AC power is delivered to the onboard charger of the EV, which converts it to DC. A DC converts the power, DC EV AC means electric vehicle supply equipment, converts the power externally and supplies DC power directly to the batteries by passing the onboard charger. Okay. If we are using a direct DC voltage or DC supply, then there is no need of any onboard converter. Directly it is supplied to the battery pack. Because we have to perform certain preconditioning on the battery pack. What is that preconditioning? I'll be saying. Then normal power charging, you can say for vehicles less than 7 kilowatt and 7 kilowatt to 22 kilowatt AC or DC. AC or DC. You can say for two-wheelers, three-wheelers, and first generation e-cars. Then high power charging greater than 22 kilowatt, less than 50 kilowatt DC, and 50 kilowatt to 200 kilowatt DC. DC charging is required because if the charging voltage is very high, a small hike will also be too much. If the battery potential, the charging potential is let's say 500 volts, If we are using AC, AC means converter, we are using converters, so converters will be converting it to DC. So there may be spikes, and those spikes can range up to 20 volts to 30 volts. This may damage the system. Hence, pure, you can say DC, it is converted to DC on the charging stations only. The charging stations will be attached with very good converters, and that can be repaired and maintained periodically. The thing that we cannot do in our EVs. Then various types of power ratings. Remember what I'm saying first, I'm saying you about all the charging requirements that are needed for, or what are the charging types and charging requirements. Then we will see how can we use those, or how can we arrange those charging standards, or how we can fulfill those charging requirements. What are the various types of chargers that are needed and charging requirements for various types of electric vehicles? What is the power rating of those chargers? Then we will see how we can integrate, or how we can assemble, or how we can fulfill those requirements. We can integrate the systems, those EVSE systems, assemble the EVSE systems, and to fulfill the requirements of our electric vehicle. Okay, we'll see those things. The electric vehicle supply equipment have different power rating or levels based on charging requirement, which in turn determines the input power requirement for charging infrastructure. Normal power AC charging. Sorry, normal power AC charging is adequate for electric two-wheelers, electric three-wheelers, and electric cars. Normal power DC charging is unique to India due to the prevalence of light electric vehicles and use of low voltage batteries in electric cars. In India, not enough DC chargers are available. AC chargers may be available, or it is available for previous generation electric vehicles, but DC charger is not available because it needs a very robust converter. Why? Because we are charging a very large system, so it should be very precise. Batteries charging should be very precise, or else we may face a lot of problems. Single phase AC chargers with a maximum power rating of 7 kilowatt are adequate for light electric vehicles and cars with single phase onboard chargers. Three-phase AC chargers with a power rating of 22 kilowatts are required for e-cars with large onboard batteries. If we have a very small onboard battery, then single phase, we can use single phase. But for large batteries, we need three-phase charging. Or else what will happen? There will be a lot of heat generation. There will be an inductance effect or reluctance effect. Reluctance effect means if in a given wire, we are continuously changing the voltage, then that, remember, whenever we flow electricity on a wire, the wire gets, or there is electromagnetism in the wire. When we try to change the current in the wire prevents that change because it has to collapse because it prevents collapsing of the magnetic field. We know in inductors, when we try to change the current, the inductors are not happy. Why? Because the magnetic field that is generated by the inductors needs to collapse itself. Again, it has to rebuild for a new current. Okay, first the magnetic field will collapse, then again it will rebuild. Hence, those things offer resistance. So single phase is good for 7 kilowatt charging, but when charging power increases, then if we are using a single phase, then there will be a lot of heat generated because of reluctance. Reluctance means the same wire, if we are changing the charge, we are changing the current, the wire will prevent any change of current. And since we are providing, or we are supplying very high current, the wire will heat up and there may be damage. You can say there may be fatal consequences. There may be a lot of damage in the system. Input power supply for normal power charging can be provided from standard electricity distribution network. Then battery swapping. Another method that we can use is also battery. You can say it is battery swapping. Generally very good for electric two-wheelers. An alternative battery recharging method that is received global attention is a battery swapping, in which a depleted EV battery is removed from the vehicle and is replaced with a fully charged one. Technology is being tried out for various EV segments, including electric two-wheelers, three-wheelers, e-cars and even e-buses. There is automatic battery charging that uses robotic arms to replace the battery, and manual swapping is also there. The battery swapping station is a standalone device in which batteries are placed and removed manually from the individual slots used by hand. Manual swapping stations are modular and occupy a minimal amount of space. These are used, used for two-wheelers and three-wheelers battery application, as the battery pack size is small and weight can be handled by 1 or 2%. So then there are two types of battery swapping methods, manual and automatic. In an automatic or in an autonomous battery swapping station, generally used for vehicles, large vehicles and commercial vehicles. A robotic arm is used in this type of swapping stations, with battery swapping process being semi or fully automated. Robotic swapping is used for four-wheelers and e-bus applications, as the battery pack are large and heavier and require mechanical assistance. These swapping stations are also more expensive and have a higher land requirement. So you can say if we use an autonomous battery swapping station, then it needs a lot of land. Or it needs a lot of space for installation. But in near future, these things will also be available, because manufacturers will be availing these things, or they will be installing these things, or they will be installing these features in their vehicle, that we can swap these batteries. Just we have to reach the station will be swapping the battery. It is very easy. This system will be very easy rather than refilling the battery. It will be very efficient also and economical. So we have seen what are the various requirements of charging and various types of battery swapping. Then let us see the power management that we have to do. Okay. So we have seen that the power ratings for various types of EVs, and depending on the power rating, we have various types of electric vehicle supply equipments. Okay. Now let us know about the power management, because let's say if we are connecting 10 EVs of 22 kilowatt, then that becomes how much? That becomes nearly 200 kilowatt. Oh, sorry, 220 kilowatt. 100 EVs, that becomes 2000 kilowatt, 2 megawatt. Okay, it becomes 2 megawatt. And 1000, it becomes megawatt. 1020 megawatt of energy is needed at a given instant. Okay, if at a particular time in a different location, if we add up or if we sum up, means because this, let's say you can say your power generating stations are there, thermal power generators are there, wind power generators are there, and you can say hydropower generators are also there, nuclear power generators are also there. They're all supplying their electricity to various segments. Someone is supplying to household, someone is supplying to industries, someone supplying to some railways, someone is supplying to some other type of industries. Okay, but which type of infrastructure is needed for supplying energy to electric vehicle? And if it is supplying, then what about the other industries that were previously that are they are utilizing? Generally, in charging stations, there will be a lot of overload. Hence, the you can see charging stations, there will be a lot of overload in power. Hence, the you can say the power generating stations or the power generating units should be able to handle all those things. Let us see how the power management is done. The total electricity demand for EVs at 33% EV penetration by rate of 2030 is projected to be 37 trillion watt hour. You can see 37 trillion watt hour of electricity demand. This contributes less than 2% of the total electricity demand across the country. Okay. We can say this contributes only 22% of the total electricity demand. But that is not the problem. It is the contribution is less, but the timing is very much important. Okay, the contribution is less. Okay, total we have 37 trillion watt hour of requirement, and 37 watt hour is reached in 2 hours, or sorry, in 2 days or 3 days. There is no problem. We are reaching 37 trillion watt hour in two days or 3 days. But if we will be reaching 37 trillion, not even 37 trillion, 37,000 watt hours in just 15 minutes, that will be very difficult. Okay, so we will discuss what are those things. Therefore, meeting the overall energy demand is not expected to be a challenge in India. Actually, there will not be any challenge. We have enough power. But when the power requirement is very high within a short period of time, then there is challenge. Actually, we are generating a lot of energy. But when the energy requirement is very high for a very short period of time, that becomes difficult to control. Let's see. However, high charging capacities for EVs and their partial connection may lead to significant volatility in their power demand. Okay. Partial connection concentration means you can say in Bhubaneswar, or you can say in metro cities, there will be a lot of EVs. In remote areas, there will be very less EVs. So you can say metro cities or the urban areas, there will be a lot of power shortage in the urban areas, or there will be a lot of load on the urban areas, load on the grid, because a lot of electric vehicles are running. So partial concentration is a problematic thing. In a short region where we have to supply a lot of power, so that should be managed properly. Combined with bottleneck in distribution capacity at local level, this can result in barriers to seamless provisions of EV charging connections and can impact grid stability for all electric consumers. You can say the distribution capacity at local level is not that developed in India. As we see that in the remote areas, the power supply is not that efficient, not that good also. So if we have to install charging infrastructure, charging stations in those areas, then it will become very difficult. Because for installing a petrol station, it is not that difficult. We just need a very big container. The container will be refilled. We need pumps. Pumps can work very easily on AC supplies, or it can be run very easily on the type of supply that we have in India. So there is no problem in installing, you can say petrol stations, but there will be very problem in installing EV charging stations, because the power requirement for EV charging stations is very standardized. Okay, and India does not have that kind of power delivery or power distribution capacity. Improving the utilization of electricity. Electric management measures and distributes the charging network planning at the feeder and network level. And at the feeder and network level can help optimize grid utilization and significantly reduce the immediate need for expensive upgrades. That means we have to upgrade. Remember, the power generating units have to upgrade or has to upgrade themselves so that they can reach or they can meet the power requirement for charging a large number of EVs. Now, the infrastructure that we have, it may not be able to supply that much amount of, so it is able to supply, but it is not able to handle the load. Remember, it can supply, but for a very short period of time, when the requirement is very high, it cannot handle those periods. It cannot handle those periods. Three means by which EV charging load can be managed. First is distributed design of charging infrastructure, passive management of EV charging load, and active management of EV charging load. Passive management of EV charging load and active management of EV charging load. What is passive and active management? Let's see. So in here, I have shown you the time of the day where the EV charging is very high. Generally, during the night time, most of the people will be charging their EV. During night time, most of the people will be charging their EV. In India also, during night time, most of the people will be charging their EV. And also during the daytime. Daytime means from 8 a.m. to 10 a.m. From 2 p.m. to 4 p.m. During, or you can say, at these times, though it may not reach these peaks, but still there will be peaks. You can see in here there is a peak. You can see in here from 12 there is a peak. Okay, and that peak continuously increases. So suddenly there will be a lot of load on the infrastructure. There is no load, no load, no load, and suddenly there is a lot of load in the infrastructure. So the infrastructure has to manage this because it is not continuously supplying that much amount of energy. Okay. But for a particular instant, it has to supply that much amount of energy. When the power requirement is constant, there is no problem. But when the power requirement is varying, then there is a problem. Why? Because the infrastructures has to manage these things. Okay. They have to upgrade themselves so they can match with the power delivery. Okay. So distributed design of charging infrastructure. A concentration of charging points at one location, especially of high power chargers, increases the load requirement of EV charging. Okay. This in turn can necessitate infrastructure upgrades when the permissible utilization threshold for a feeder is exceeded. Hence, it is recommended that charging infrastructure is implemented in a distributed manner to limit the power demand for charging at any location. Okay. Okay. So what we have to do? We have to distribute the charging infrastructure, and the distribution center should not be very. You can say this should not be located at a very large distance. The distance between two charging infrastructures, charging sessions should not be very high. It should be managed properly. Where should be the means where we should install the charging stations where there is lot of traffic, means where the traffic can be handled, where there is lot of area available, and the electricity that is also available is of good quality. There is no industries nearby that get hampered because of lot of load. Hence, it is recommended that charging infrastructure is implemented in a distributed manner to limit the power demand for charging at any location. Then passive management of EV charging load. Passive EV charging management entails influencing the charging behavior of EV users through specifically designed electric tariff instruments. Okay. Then time of day, that is tariff are designed so that EV charging is more expensive during peak hours to reduce overloading the electricity bill. So what will happen? Let's say if I have to charge just 5% or 10%, that means I have to travel a distance, very short distance. For that, I need 5 to 10% of charge. So I'll not be charging it during high or during peak hours. I'll be charging it after some time. When the peak hours are over, at that time I'll be charging. When I have very less charging requirement, I'll not be charging during peak hours. So this is passive management. That means the tariffs of charging will be managed. That means if I am charging during the peak hour, I have to pay more price rather when I'm charging during non-peak hours. Time of day are effective, tariffs are effective at managing EV charging loads without excessive financial burden on EV owners or CPUs. In active charging. Active charging management involves remotely controlled EV charging that responds to trigger like charge in tariff, power demands, etc. Depending on the inputs, EV charging sessions can start or stop and charging levels can ramp up or down automatically. Smart chargers with specific capabilities are needed to carry out active EV charging. Active EV charging means when the load increases, the tariff will increase. Means you can say means instantaneously the tariff will increase. Or there is real-time management. Okay. The management is real-time. It is not passive. That means the tariff will be set, then we will be charging. No, it is managed in real time. For that, we need smart chargers. Both active and passive smart chargers. Smart chargers can also handle passive management instruments like time of day tariffs and more dynamic regimes like time of use tariffs, in which electricity tariffs are adjusted in real time based on demand. You can see the tariffs are actively managed. They are not passively managed. Okay. Then this is the charging load for California. And this will be same for India also. Okay, because day and night and working time is similar. In India also people are working from 8 a.m. to 10 p.m. In California also 8 a.m. to 6 or 7 p.m. 6 p.m. So time will be, it will differ somewhat, but not significantly. So India will also face the same type of charging distribution. In making EV charging smart, how can we make the charging, or how can we go for smart charging? Smart charging encompasses a range of functionality and capabilities for private charging, and electric vehicle supply equipment with basic functions is adequate for programming according to time of day tariffs. For more advanced solution at commercial charging facilities or rapid charging hubs, a wider range of functions is needed to enable dynamic load management. Respond to TOU, time of use, tariff signals to operate different subscription plans for seamless charging transactions. That means there will be various types of plans that you want to charge, you want to have a high speed charging, low speed charging, or any intermediate speed charging. Means what should be your charging rate? There maybe you can say in a charging station there will be 4 locations where you want to charge. Fast charging, or you can say not standard charging, not slow charging, standard charging. Fast charging, standard charging, then low charging or slow charging. Okay. So where you want to charge? You want to go for fast charging where you will be charging within 10 minutes. You want to go for standard charging where it requires 30 minutes, 30 to 45 minutes for 80%. Or you want to go for low charge. That means which takes nearly 1 hour or 1.5 hours to fully charge, or for 80%. So where you want to charge? For this we need smart chargers or smart charging systems. Okay. And the tariffs will also be maintained. That means if there is a lot of overload for standard charging, the standard charging price will go high. If there is overload in low charging, the low charging price will go. You can say it will rise or it will increase. If there is overload in fast charging, this price, fast charging price will also increase. An electric vehicle supply equipment with advanced charging capabilities has the following characteristics. It can be programmed to respond appropriately and autonomously to signal from DISCOM. DISCOMs means your electricity tariff, generally controlled by the DISCOM, Central Management System, to coordinate with time of day and time of usage tariffs. It can be monitored and managed over an app. You will be having an app that will be connected to the DISCOM servers, where you can see what is the current tariff at what price you are charging your EV and how it is going to change. After 5 minutes, what will be the price? Before 5 minutes, what was the price? So that you can manage your cost properly and charging also. It is equipped with GPRS, 3G, 4G or wide connection and is connected to cloud service. It shares a data connection with an EV and charging network. It is compatible with back-end communication protocol. Okay. Backend means it should be all the type of data that are stored for charging. That means it can use the data that are stored in the servers and it can access the data and it can work on those data also. That means backend connections should be proper. Then there are various types of communication protocols for charging, for smart charging. Smart charging at scales requires uniform communication architecture to allow interaction between different levels of systems. That means between various types of EV charging supply equipment and charging networks. Between different charging networks and between the central management system and distributed energy resources management system, DERMS, hosted by DISCOM or a third-party aggregator. That means the smart charging system has to communicate on different levels. It has to communicate with the servers of central management system, distributed energy resources management systems, and DISCOMs or any third party that is there. It has to communicate between all those things to set up the tariffs and to have the correct types of supply for the required vehicle. Two types of communication systems can be implemented for smart charging, that are EVSC, CMS communication, CPO, CPO communication, CMS, DERMS, utility connection. So what is a EVSC, EVSC, CMS communication? The open, you can say the OCCP, you can say Open Charger Point Protocol, is an open source freely available standard that enables communication between EV, SC and CMS. CMS means your central management system that controls all the charges of a given location of a given area. It allows interoperability, interoperability, sorry. This interoperability, it allows interoperability among different charging equipments, software systems, and charging networks, allowing user to switch between charging networks. It has a feature for device management, transaction handling, security, and smart charging. Then CPU communication. This is our EVSC and CMS communication. Then CPU. Okay, that means charging point protocol. The Open Charge Point Interface Protocol, or OCPI, supports information exchange between e-mobility service providers. E-mobility service providers means, remember, when you will be having an electric vehicle, a lot of apps will be released in order to charge the things. A lot of new industries will be coming up to control these communications. Okay, there will be service providers that will be connected, that will be connecting your vehicles to various types of networks. Though we can use Starlink is, or you can say Starlink is generally used for these things. Okay, Starlink, that is generally not Sterling, Starlink. Okay. Generally, it is generally used for these things, for communication between the EVs and various types of networks, to enable automated roaming between charging networks for EV owners. Supported features include charging point information, charging session authorization, tariffs, reservation, roaming, and smart charging. That means it will follow you where you are, what is the, how much, that means, remember, if the system has information about your vehicle, then it can properly manage the load. Let's say a given area has 1,000 vehicles and the system is connected to all the 1,000 vehicles. So it can know that yes, these vehicles needs charging. They are at a given location. The user is developing an intent to charge, so that it can properly manage the tariffs and also charging systems. If you are surprised, if your vehicle is not connected to any cloud or it is not connected to any network, then you will be arriving at a charging station by surprise. Okay, but I want to charge. They have no information. Okay, so you did some charging. I have no information. Previously, for petrol vehicles, it is not that a problem because surprise is not a problem. Okay, for petrol vehicles, surprise is not a problem because the refilling time is very less and the petrol stations are managed properly. But for charging stations, because the charging stations needs to have a wide variety of features, hence it has to manage a lot of traffic. Hence, nothing should be by surprise. The vehicle should not be reaching you by surprise. The network or the central management system should previously, it should have information that yes, this vehicle XYZ may reach at station number 5 for charging, may reach, or it may go for station number 6 for charging, so that that station can manage its traffic properly. It can know that yes, another vehicle will be approaching in 2 minutes, another vehicle will be approaching in 3 minutes, another vehicle will be approaching in 4 minutes. You can book charging also. Pre-booking is also there. That means, let's say you have seen that I have only 10% charging left. So you will book one slot. Okay, at 3:15 to 3:45, I will be charging. So you can book slots also. But still, they don't need any surprise. Okay, slots are booked, but you may reach there beforehand. Then you have to wait. Then there will be a lot of problems. So they cannot make you wait. Those slots are also available. When in urban areas, slots are available. But if you are moving from one region to another, the slots timing may vary. You cannot accurately follow the slot timing. So there will be certain free charging stations. Free means there is no slot. You just come, then they will be connecting the charger, you will be charging, then you will be leaving. There is no slot booking. So for those things, if any new vehicle arrives, then that is a surprise. Okay, I have another vehicle. I have another vehicle. So I have to manage the powers properly. Hence, you can see if there is communication protocol or there is communication between the electric vehicle and the central management facility or system, then it is very good. Okay. Then integrating the EV charging in grid planning. That means whenever we'll be planning our grid, that at this region I have to place or I have to install a new grid, then I should manage or I should plan the grid accordingly. That means how much amount of EV this system or this region will be handling. Now 100 EVs are working, but in 10 years or 20 years, nearly 1,000, 2,000 or 10,000 EVs will be running in this region. So I have to install the grid in such a way that there will be no overload. Okay. You can say readiness of electric grid to cater to EV charging demands is critical to achieve rapid and large-scale transition to EVs. Only when the grid planning is proper. That means the new grids, you can see it is Tata Power has taken, you can say, Tata Power has taken the charge of upgrading the grids or upgrading the electricity supply units throughout the country. It is because of these things, so that it can effectively plan out how to install the grids at various locations. However, going forward, DISCOM planning process for grid upgrades and network expansion will need to account for EV charging loads. Sorry. Application of smart charging measures can help manage EV charging loads to a certain degree without the need of grid upgrades. If we have advanced smart charging, then up to some extent, these things can be managed, but not for a large extent. Okay. Going forward, DISCOM's planning process for grid upgrades and network expansion will need to account for EV charging loads. The impact of EV charging on power demand. What is the impact? Okay, just just 1 minute, guys. So is my screen visible?
No, sir.
Okay. Okay. Impact of EV charging on power demand. The study EV, a new entrant to Indian electricity consumer basket by Alliance for an Energy Efficient Economy, evaluated the seasonal impact of charging infrastructure for 10,100 EVs, comprising of 7,100 electric two-wheelers, 1,550 electric three-wheelers, 1,350 electric four-wheelers, and 100 e-buses on a peak power demand of each of 4 discoms in Delhi. The study developed an Excel-based model to evaluate the charging indoor profile of a discom due to EV charging based on the following input data. So they have created a study, or they have studied, or you can say they have studied the various types of power requirement by various types of electric vehicles in Delhi. The load data for DISCOM for different seasons of the state load dispatch center were studied. EV population scenario based on publicly available projected data were studied. Vehicles and large specifications, vehicle and charger specifications for different EV categories were studied. And the charging requirement and time-based charging patterns for different EV segments are also studied. So studying all these things, they have found out what is the impact of EV charging on power demand. The study indicates that immediate EV charging demands consists only a marginal fraction of the total demands in a DISCOM service area. However, even at this stage, EV charging can potentially excavate peak loads or fill up of power sorry, and fill out the off-peak hours of electricity demand based on EV charging patterns. If the patterns are not properly maintained, if there is that means if the power management is not properly maintained depending on certain patterns, then there will be a lot of problem. Power cut will be there. Some of the industries will not be getting enough power. There will be a lot of uh, problem. Further, when the study considered approximately 10,000 EVs in a DISCOM service area in Delhi, where there are more than 23,000 EVs registered in Delhi in 2019, this figure expected to grow more than 2 lakh. Okay. EVs registered per year by 20. That means only Delhi will have 2 lakh EVs. At the projected rate, EV charging demand as a component of total electricity demand in a DISCOM service area is expected to grow rapidly. The impact of EV charging is expected to be more pronounced at the distribution transformer level, which can be projected through impact assessment of localized charging loads on grid infrastructure at feeder level. So if we consider the EV charging, is expected to be more pronounced at the distribution transformer level. Distribution transformer level means, as we have seen that uh, for various cities, for various locations, transformers are there. They are generally used for household supplies. So you can say the impact will be very much at those levels. The impact will not be too much. Remember, when the transformers are able to handle the loads, then the problem will be there for power generating units or for other type of transformers. But when the local transformer is not able to handle the load, then obviously the problem is at the local level. Okay. That means currently the transformer that are installed in your city, if the transformer is not, or in your locality, if that transformer is not able to handle the load, then first problem occurs over there. That means you have to replace the transformer. Then you can say a broader level of changes can take place, but localized changes will be done first. Hence, localized transformers will be affected first. The localized grids will be affected first. This is what it is saying. Impact of EV charging is expected to be more pronounced at distribution transformer level, which can be projected through impact assessment of localized charging loads on grid infrastructure at the feeder level. Okay. Then impacts of EV charging on power demand. You can say time of the day. On Delhi, this is done on Delhi. On different days. Sometimes during, you can say, 2 p.m. or 3 p.m. to 5 p.m. there is a peak. At night time there is a peak. Night time there is a peak. Night time there is a peak, and in the daytime there is also peak. So you can see these are the various types of readings or study that are available. And you can say by studying these things only, we can able to better manage our charging infrastructure. But we are able to better manage our charging infrastructure. Remember, it is an ongoing process. It is not a fixed process. It is continuously growing. So enough data is required so that we can reach our targets and goals very effectively. Then what is preconditioning? Remember, if we'll be asking, sir, you have said that 2% of the total energy requirement is there for EVs. Then can't we just upgrade, or can't we just reach those requirements easily? Yes, we can reach, but there is another thing, that is vehicle preconditioning. Now, a lot of manufacturers are asking for preconditioning in the vehicles. Actually, the manufacturer, not a lot of customers are asking, and manufacturers are also intending to apply or to have preconditioning in vehicles. And that preconditioning is done at the charging station. And what is the preconditioning? Preconditioning of EV for battery charging for a future trip. Pre-coiling, not this is coiling, this is cooling. Pre-cooling in summer, pre-heating in winter. Let's say, you can say when you are running your EV, your battery is too much hot. That means your battery is generating a lot of heat. Your battery has heated up a lot. You are driving in, let's say, you're driving in, let's say, Delhi. Okay. You're driving in Delhi where the temperature is very high. Hence, your battery pack temperature will also be very high. When you connect the charger to a fast charging system, then the fast charging system will again raise the temperature of your battery. Let's say if your temperature of the battery is 45 degrees Celsius. 45 degrees Celsius. When you connect fast charger, it may go up to 60 degrees Celsius or 70 degrees Celsius. So how to cool down these things? If you are utilizing your onboard cooling system, that means the cooling system that is cooling the battery when the vehicle is running. If you are utilizing your onboard cooling system, then it will extract energy from the battery pack. It will extract energy from the battery pack. Okay, onboard energy systems. It will extract the energy from the battery pack. Okay. So how to do it? Or you can say if that is extracting energy from the battery pack, then it will take a lot of time to recharge the battery, because the cooling units are trying to cool down your battery pack. Hence, on the charger only, okay, on the charger only, cooling fluids will be supplied to cool down the battery pack. Okay. On the chargers, there will be cooling fluids to cool down the battery pack. In summer, in winter, on the chargers only, there will be heating fluids to heat up the battery. Because generally for lithium ion battery, the operating temperature is from 20 degrees Celsius to 30 degrees Celsius. What needs preconditioning? EV battery for functionality, cabin for passenger comfort. Okay. Let's say at a at your office, you have connected the vehicle to charging unit. So when your office is over, so you should you want your vehicle to be cool and cozy, or it should be at a very good temperature, so that when you will be entering the vehicle, you'll feel very good. So for that, preconditioning is required, and that preconditioning is provided by the charging station. They will, you can say, they will charge you for this. The amount of energy that is required for preconditioning, they will charge you for this. But preconditioning is required so that your battery pack will work properly, and also you will have, or there will be passenger comfort. When the passenger will be opening the vehicle for driving, then there will be a very good temperature inside the vehicle. In the summer, it will be very cool, or you can say that inside temperature will be very low. Not very low, it will be lower than the outside temperature. And during winter, the inside temperature will be, or inside will be warmer than the outside, so that there will be passenger comfort. Lithium-ion batteries are very sensitive to temperature. Optimal temperature range is from only 20 degrees Celsius to 30 degrees Celsius, similar to human comfort zone. Discharging the lithium ion below 5 degrees Celsius and above 45 degrees Celsius severely reduces performance. If we discharge the lithium battery, discharging means if we are using the lithium battery below 5 degrees Celsius or above 45 degrees Celsius, then the lithium battery shows degradation in performance, or it degrades very rapidly. Hence, we have to cool down or heat up the lithium ion battery pack to work within the optimal temperature region, that is 20 degrees Celsius to 30 degrees Celsius. Why preconditioning is so important? Installed cooling heating capacity is limited. Okay. That means the cooling capacity that is installed on your vehicle, it is very limited. Okay, it is very limited. Why it is limited? Because when you are charging a battery pack for or within 15 minutes, you will not be utilizing all the energy within 15 minutes. You will not be utilizing on all the energy within 15 minutes. Let's say your charging time is 15 minutes. So you will not be utilizing all the energy within 15 minutes. You will be utilizing all that energy in 4 to 8 hours. So the amount of energy that is being utilized during discharge is very less than the amount of energy that is utilized, that is being used for charging. Hence, the installed or the onboard cooling units cannot cool down the battery pack quickly during charging, because the amount of energy that is utilized for charging is very high. Hence, there will be a lot of heat generation. But the amount of energy that is utilized for driving is much more lower than charging. Hence, the cooling systems can work very efficiently for those things. Okay, then EV tends towards large compressors. Part loading efficiency become important. Amount of electric energy stored in battery is limited. Then drive range drastically reduces at extreme ambient temperature, low battery performance, energy spent on thermal management. So these are some of the reasons why we need battery preconditioning. The preconditioning of passenger cabins works for both heating and cooling. Make use of available energy sources while EV is plugged in. Reduce energy intensive vehicle warm up, cool down, most beneficial for short drives. Autonomous vehicle trends, you can say. In autonomous vehicles, we will have cabin load will increase for electronics cooling. Since autonomous vehicles will have lot of electronics installed. We'll be having monitors, we'll be having charging units, a lot of electronics will be available or will be there for autonomous vehicles. And the electronic components needs to be cooled down. Okay, we have to cool down those electronic units. Hence, preconditioning is required. If you just leave the vehicle with all the electronic components switched on without any cooling of passenger cabin, then the passenger cabin will heat up. Then increased sensitivity for temperature range. Since the EVs are now becoming very much sensitive to temperature change, they are becoming very much sensitive to temperature change. Hence, we have to maintain the temperature properly. Hence, preconditioning is required. The preconditioning of EV battery. Remember, this is the preconditioning of passenger cabin. Okay, we need to precondition the passenger cabin because a lot of electronics will be there inside the passenger cabin that has to be cooled down. And as human, we are also sensitive to temperature. We don't want extreme high temperature or extreme low temperature within our inside our cabin. We need very optimal temperature, or we need good temperature within our cabin. Then preconditioning of EV battery uses active heating and cooling concept to maintain battery temperature in range of 20 degrees Celsius to 30 degrees Celsius. Below 20 degrees Celsius, sluggish chemistry, dendritic growth. Above 60 degrees Celsius, irreversible damage occurs to SEI. SEI means solidified electrolytic interface. Layer and electrolytic breakdown, damage to separators. If we are using lithium ion, then they will have very sluggish chemistry and dendritic growth when the temperature is below 10 degrees Celsius. If the temperature is above 60 degrees Celsius, then there will be irreversible damage to the solidified electrolytic interface. In our lithium battery, we have a solid electrolytic interface. In here, we have our electrolyte 1 for cathode, then electrolyte 2 for anode. The ion exchange will take place between this solidified electrolytic interface. Okay, then ion exchange will take place between this, or you can say within this solidified electrolytic interface. And if we use the battery above 60 degrees Celsius, there will be irreversible damage to the layer. Okay. Then battery charger and heat rejection. Level 1. If I'm charging the battery at home, then I should have a 120 volt AC supply, 16 ampere of current supply, and the charging units you can say should be less than 2 kilowatt. That means it should be. Is my screen not visible? It should be less than 2 kilowatt hour. Then level 2, 20 kilowatt hour. Level 3, you can say 480 volts, and it should be greater than 20 kilowatt hour. And for next generation, that is extreme fast charging. Extreme fast charging is generally for 800 volt DC. Charging time is only 7.5 minutes to charge for 200-mile range, and the system is 400 kilowatt. Normal driving, you can say during normal driving, there is only 3 to 4 kilowatt of heat rejection from the battery. But during extreme fast charging, there is 20 kilowatt of heat rejection from the battery. Hence, the onboard cooling systems cannot reject or cannot absorb this 20 kilowatt of heat from the battery in a very short period of time. Hence, we have to provide coolants through our charging units only. Okay, through our charging units only. Then liquid cooled charging cables. That means our charger will have liquid cooled charging cables where the coolant will be supplied to charge the battery. Remember, if we are charging the battery using extreme fast charging, then the battery will heat up very fast and we have to cool down the battery. Okay. Normal driving, only 3 to 4 kilowatt can be handled by onboard cooling system. But when we are going for extreme fast charging, then the onboard cooling system cannot be utilized. Okay. And how to implement preconditioning? There are various types of EVs uses vehicle cooling heating systems, power externally from the battery, heat source or for heat pump, air frosting, electronics battery, waste heat, PTC means positive thermal coefficient devices, possibility for free cooling, battery cooling concepts. These are battery cooling concepts. You can use a chiller, a PTC heater, a refrigerant DX cooler, okay, and liquid cooling in order to recharge the battery. Okay. Then what are the challenges and opportunities affecting preconditioning? Refrigerant selection. What type of refrigerant should be using? Okay. What type of refrigerant we should be using for our cooling system? Then reliability. Can these systems be reliable? What is the environmental problems? Okay. Limitation by capacity of onboard cooling heating systems. Large components or increased performance of existing part, increased available heat flux through direct contact evaporation. So what will happen is, remember, previously batteries were arranged in modules. Then modules were used to create the battery pack. But now the batteries or the cells are directly immersed in cooling fluids. Okay, the cells are directly immersed in cooling fluids. That means all the cells, they are directly in contact with the cooling fluids, so that there will be direct contact evaporation of the cooling fluids, thereby increasing, or you can say we can have very fast transfer of energy or transfer of heat from the battery to the cooling fluids. Okay. Okay, Mohideen, let me just end these things, then you'll be asking more questions. Remember, all the cells are directly in contact with the cooling fluids. There is no cooling jacket. Cooling jacket is there, but actually cooling jacket is ever outside of the battery pack to cool down the casing of the battery pack. But inside the battery pack, cooling, we can say all the cells are immersed in the cooling fluid, so that there will be very efficient transaction of heat between the cells and the cooling fluid. Then direction of future development. Technology drivers, shortcoming charges, reduced losses, breakthrough in battery technology with reduced heating cooling demands, energy efficiency. EVs are no longer autonomous systems integrated into surrounding systems and building. That means EVs are no longer autonomous. Okay, autonomous means the EV is connected to its surrounding. The EV is connected to network. The EV is connected to your household. It is connected to your phones. It is connected to your friend's phone. It is connected everywhere. Hence, these are not autonomous systems. Okay. These are IoT devices. These are components of IoT devices. EVs are now components of IoT devices. They are not autonomous. That means it will not be working independently. It will work dependently, or it will work with dependency on other systems. Okay. So all these things are required for the future. So what are the things that we have covered in this session? Let me just show you. So overview of India's charging infrastructure, vehicles available in India and various types of charging requirements for those vehicles. Then power ratings of all the vehicles available in India, various types of battery swapping methods, then power management that can be done on the grids or on the power generating units, then various types of power management, passive management, active management, and then charging load management, then installing smart charging stations, then various types of communication protocols so that the smart charging stations can run properly, then integrating EV charging in grid planning. That means whenever we'll have a new grid planning, then we have to integrate EV charging in that grid planning. If there is a new government project for developing a new grid, then EV charging should be integrated to the grid. Then impact of EV charging on power demand. That means what are the various types of impact that the charging grid will come across because of power demand. Then what are preconditioning in vehicles? Preconditioning means when we will be installing charging stations, then we have to install preconditioning also. That means the charging station should also be able to cool down your battery pack. They should be able to precondition your vehicle. Let's say 15 minutes of charging. Okay, you have connected the charger and the driver don't want to sit inside the vehicle. It wants to have a snack. It wants to have a coffee. So it is connected. You can say it will connect the charger, or it will just place the vehicle on the charging station where automatically it will take the vehicle to the charging area. And for that 15 minutes or 20 minutes of charging, the driver wants to have a little snack. And when he enters the vehicle should be cool or it should be warm enough to drive. If it is hot, then the vehicle should be cool enough, or the cabin should be cool enough. If it is cold outside, then the cabin should be warm enough, so that he can have his snack properly. Okay, that means the driver. Okay, the driver wants. Okay, my charging time is. You can say in the app it is showing that my charging time is 30 minutes. What I will do for 30 minutes? Will I just sit inside the vehicle? No, I should roam. There will be a shopping mall near the charging station. So I should shop for 30 minutes or for 25 minutes. I'll be shopping. Now, when he is there shopping, there should be preconditioning. The charger or the charging stations should avail the preconditioning so that when the driver again enters the vehicle should be properly conditioned. The temperature should be proper, the battery should be managed, all the servicing, small servicing that are required should also be done. Okay. Hence, preconditioning is required. And it can be done very easily in electric vehicles. If it is a engine, IC engine, then preconditioning is difficult. But if it is a EV, preconditioning is easy. Then why can't we integrate those things? But for integrating those things, the charging infrastructure should be managed properly.